Hello everyone, my name is Kevin Dick and I'm a postdoctoral research fellow in the Department of Systems and Computer Engineering at Carleton University, and I'm excited to be presenting you this vision paper that I wrote along with my co-author, Dr. James Green, entitled Emergence of an Autonomous Vehicle Secondary Data Market for Breakthrough Applications. The prophesied circulation of fleets of autonomous vehicles, otherwise known as AVs, in urban and rural environments promises unprecedented opportunity to remotely sense streetscapes at fine spatial and temporal resolutions. Autonomous vehicles employ a variety of onboard sensors to capture information about the local environs for the primary purpose of vehicular navigation. However, in this work, we propose that these data may find a further secondary use in a broader array of what we denote breakthrough applications, that is, technologies and use cases that are enabled through the fine-grained spatio-temporal sensing of this lived environment. Consequently, there is the opportunity for a market of the secondary use of these AV-collected data that is emergent, and a cloud-based architecture to manage the collection, processing, and communication of these data is required. And so what's exciting is the growing trend of the use of machine learning models to extract desirable secondary information from these fine-grained spatio-temporal data. We will then enable these unprecedented global scale and time series studies. And so in this work, we outline the essential elements of this vision, and we introduce the utility of what we call the Remote Sensing AV-based Informatics Layer, or RAIL, and the various breakthrough applications that it would enable. And so before getting too ahead of ourselves, it would be important to start with a preliminary existing technology very similar to what we're envisioning here. And so the last decade has enjoyed this prolific integration of Google Street View, or GSV, imagery in a diverse array of industry, government, and academic applications. Some notable examples can be seen in health research, criminology research, the detection of gentrification in cities, and even estimating socioeconomic characteristics within neighborhoods broadly across the United States. And so Google Street View imagery and data represents, to the best of our knowledge, the most globally comprehensive resource of street-level visual imagery in the lived environment. And this is done in large part through the deployment of fleets of daily operating Google Street View vehicles. And so Google exposes much of this rich resource through an application programming interface, or API, as part of its cloud platform. And this has provided a wealth of opportunity for researchers to leverage Google Street View imagery for a number of different remote sensing applications. Moreover, there have been quite a few recent dramatic advances in the use of artificial intelligence and cloud computing, notably deep machine learning models that can be individually trained to detect specific elements of interest in the natural environment and applied to those data acquired in the future. But what's unfortunate with Google Street View imagery is it provides only a very temporally coarse-grained resolution of imagery, which effectively limits its utility in longitudinal or time series applications that would require both a high spatial and temporal resolution. And there's a specific example of this. There's a large-scale study done in South America that was assessing Google Street View sampling, and it reported a dramatic variation in mean image age. At one extreme, the mean image age ranged from something as small as 9.3 months in San Miguel, El Salvador, whereas the maximum mean age was 116 months, which was approximately 10 years. And so the standard deviation also varied dramatically, but what this effectively tells us is that we cannot be guaranteed to have fine-grained temporal imagery in specific locations through Google Street View imagery alone. And so what's exciting is that there's this prophesied circulation of fleets of autonomous vehicles, or AVs, in urban and rural environments, and we are basically on the cusp of a paradigm shift in remote sensing applications. Effectively, as these highly instrumented vehicles coordinate their circulation within urban environments, they'll be necessarily sensing the environment for the primary purpose of navigation. However, these sense data streams might find a secondary use in providing a fine-grained spatial and temporal resolution of such streetscapes imagery. What's most exciting is this concept of secondary use of data has been adopted beforehand in other fields and generated entirely new avenues of investigation. And of course, while the economics of autonomous vehicles are actually something that are regularly discussed in the literature, to the best of our knowledge, there's no mention of the market for AV collected data that has yet been proposed as an additional stream of revenue. And so since AVs are typically outfitted with a broad suite of sensors for the primary purpose of navigation, these data might find their secondary use by the nature of there being a fine-grained collection of spatio-temporal data from fleets of such vehicles. And this mobile fleet-based network would complement other types of remote sensing networks or data sources that have been used traditionally. Things like satellite imagery have traditionally been collected for the primary purposes of tracking weather patterns, and yet have enjoyed widespread integration in a number of secondary applications. Satellite imagery, by its nature, has high spatial coverage in that it can capture large geographical areas. However, it has low temporal coverage given the need to be over a certain location at a certain point in time while capturing imagery. And this is in complement to something like camera networks or CCTVs that are stationary. While they have high temporal coverage in that they can record near real-time data, they have low spatial coverage in that they're limited and immobile. One study examined the sensing power available from a sensor-equipped vehicle fleet based on its ability to cover a sufficiently large fraction of a city's area during a given time period. And with fleets of AVs circulating regions around the world, we could expect petabytes worth of digital information to be collected. However, only fractions of those data will be required for any given application. In the vast majority of cases, only a small sampling of these data is required to achieve an accurate estimate, and given the nature of these data streams, it's necessary that these be sampled both spatially and temporally. In some of our previous work, we had proposed the Systematic Street View Sampler, or S3 framework, to systematically sample the available Google Street View imagery in a given region to generate specific datasets uniformly sampled from all available data and in accordance with user-defined preferences for a given task. This sampling strategy is useful to the static spatial domain alone, as is the case with Google Street View imagery, but it must now be extended to the continuous time domain. One approach might consider the concept of freshness of sense data and devise a sampling strategy based on available spatial window within a moving window of time. And in order to leverage these data and apply a sampling strategy of choice, we foresee the need for a platform to collect, manage, and analyze AV data in the future. And in this paper, we define the remote sensing autonomous vehicle-based informatics layer, otherwise known as RAIL, as such a potential platform designed to integrate with the infrastructure of AV companies and enable them to expose their AV sense data through a pay-per-use API. And so what is now most exciting is anticipating what kind of breakthrough applications will be enabled through such a platform. And so we will now discuss some of those emergent ideas based on certain trends in the literature and introduce what a certain natural language-based query or API call could look like for such an application. And so the first of our breakthrough applications are the concepts of a four-dimensional street view and also this new potential era for personalized gaming. At present, Google Street View currently enables an individual to digitally visit a location in a point-and-click manner. However, with autonomous vehicle sense data, one would additionally be able to conceptually scroll through time. Moreover, with the emergence of neural radiance fields, otherwise known as NeRF models, the scientific community has successfully modeled 3D reconstructions of the real world from multi-view two-dimensional Google Street View images. In an exciting demonstration of this technology, a collaboration between Waymo and Google Research demonstrated through their paper denoted BlockNeRF that with the synthesis of AV-sensed imagery of a location, high-fidelity three-dimensional constructions are now currently possible. And what is then most exciting is that the gaming industry could directly benefit from this type of service, given that video game environments could be dynamically rendered in near real time and in relation to an individual's location, assuming that there is a nearby circulating fleet. And so customizing a game's environment to an individual's geographical position would herald an entire new era in personalized gaming. And so a natural language query to generate such an environment might have as a form something like render the current 3D environment of Times Square. Its equivalent API call would look like something as follows: generate underscore environment with the parameters Times Square and a certain time value such as now. This second breakthrough application, and the one that is perhaps most controversial, is for remote policing applications, largely for their risk of possible human right violations. A current notable example of the secondary use of a vehicle's sensor systems in support of law enforcement is by Tesla. It has a sentry mode which monitors and records vandals around its vehicle. A similar dynamic application would be the accrual of evidence leading up to a roadside accident, that is to say, requesting data from proximal AVs in the seconds leading up to the accident that may provide multiple perspectives to piece together a coherent coverage of that accident. And then more broadly, during something such as an active Amber Alert, autonomous vehicles could be activated in this quote-unquote sentry mode to read the license plates of all nearby vehicles and alert authorities if the targeted vehicle is detected in near real time. And thus, an example query in natural language might have the form, among all autonomous vehicles, locate the vehicle with license plate ABC123 within New York State and report the results. Its complement API form would have this function that is perhaps activate sentry mode, the fleet including all autonomous vehicles in searching of a specific parameterized plate within a certain region, and to set certain parameterized values such as alert hits to visualize and make easily interpretable the results of such a query. The third general class of breakthrough applications are for the near real-time monitoring of population and/or environmental elements. The lived environment can be monitored for information extractable from the application of machine learning models, that is to say, the inferences made by these models for detecting certain elements in frame. In an exciting example, Gebru et al. Demonstrated that fine-grained car detection in Google Street View imagery could effectively be used to estimate the census and voting patterns. Since several common tasks of detecting environmental elements, such as person counting or vehicle detection, are likely to be frequently required to respond to requests, for example, things such as census estimation, we would propose that such tasks could be implemented through an edge or fog computing layer. And so one such application query might look something along the lines, and this is for those of you familiar with the popular Montreal restaurant La Banquise, would be how long is the current lineup at La Banquise, and its equivalent API call would have a function such as number of people in line. We would define the specific place, the certain point in time, and then even allow for things perhaps as a tolerance, a sliding window of approximately 3 minutes within which we would want that estimate. The fourth general class of breakthrough applications would simply be for studying cityscapes. It's quite intuitive to envision the extension of a simple vehicle-pedestrian counter to be something much more sophisticated as a machine learning model, such as recurrently segmenting complex scenes, both within or across various cities. And so many studies actually already leverage static Google Street View imagery to this purpose, and we would be extending a lot of these studies to include the temporal domain. Some notable examples might include things like determining how accessible a city is through curb cut detection, or surveying greenery and tree coverage, or for things like flood or pollution monitoring. In previous work, we've actually proposed how these data could enable the study of difficult to perceive events, or for types of events that might occur on timescales beyond human perception. One such example is the passive monitoring of electrical infrastructure. And so one such query could be something along the lines of plot the locations at 100-meter resolution of all leaning utility poles of at least 5 degrees throughout Ontario, Canada, as of today. And while quite complex, it could have an API call with a function, say, assess electrical infrastructure, where each of these terms are parameterized. A fifth breakthrough application would be for something like road-based parking or charging station search. So in addition to monitoring visually apparent infrastructure from the road, near real-time knowledge of the availability of street parking is highly desirable and actually a service that benefits AVs and non-AVs alike. In this particular case, the data freshness, that is to say the recency of extracted information, is important given the dynamic availability and competition for parking spaces. So therefore, methods to automatically detect parking spaces from Street View streams are things that already exist, and then moving these models to the autonomous vehicle's edge or fog layer would enable the near real-time communication of this information to circulating vehicles. The example query in this case would be to find me an empty rapid charger for my AV within 5 kilometers of my current location, where the corresponding API function would be finding the EV charging station at a certain location within a certain proximity and with a certain freshness of that data, that is to say, within the last 5 minutes. The final breakthrough application that we discuss in this paper is the idea of supporting data collection within crowdsourced apps. That is to say, many mobile apps rely on crowdsourced data to update their databases and therefore are dependent on the whim of contributors to notify their updates. Popular examples of this include the map event annotation of the Waze GPS app, that is for things like stop cars, road construction, car accidents, or police presence, in addition to the Gas Buddy app that relies on users to manually submit the gas price information for fueling stations around North America. As demonstrated in some of our previous work, a vehicle with cameras on it driving past street gas prices could actually apply a machine learning model to extract and read the gas price information and report this information to the cloud. Therefore, services leveraging this API would be guaranteed to have the most up-to-date gas price information available. The example NLP query in this case is quite simply, what is the price of high-octane fuel at gas stations within 5 kilometers of my current location, and the corresponding function call, something along the lines of update gas prices with a specific grade, a specific radius, and a certain percentage of freshness of that information. Crucial to realizing these applications is the consideration for the storage requirements of AV-sourced data. Under the assumption that AV fleets are continuously circulating globally and contributing their data to a cloud-based repository, what we would denote in this case as the passive monitoring economic model, a simple thought experiment reveals the gargantuan magnitude of requisite storage infrastructure. Let's first consider a single vehicle with a single forward-facing camera collecting video imagery at the conventional 24 frames per second with a colored 1080p resolution, wherein each compressed JPEG image requires an estimated 500 kilobytes of storage. Concerningly, a single AV might generate upwards of 6 terabytes of imagery in a single week. A modest fleet of approximately 1,000 AVs would escalate the storage requirement into the low petabyte range per week, and running for an entire year, this would require over 300 petabytes of storage. Fortunately though, much can be done to reduce this overall storage requirement, making the holistic management of AV-sourced data possible. Foremost, the above thought experiment is framed to collect maximal imagery at every given point in time, that is, all 24 frames available in a given second. Storage could be reduced by a factor of 24 if only a single frame is retained to represent a given second, a concept that we denote as diminishing temporal resolution, or DTR. Secondly, many applications will not benefit from imagery sourced during the evening or night. Many discernible objects within streetscapes become imperceptible outside of daylight, and thus collecting imagery outside of daylight may be less profitable as the data storage costs increase with dramatically fewer application usages. Thirdly, we can limit the spatial collection of data. That is, if another AV has recently sensed a given location, again, this is a measure based on data freshness, we could use this as a gating mechanism to prevent duplication of space-time imagery through vehicle routing. Fourthly, an organization might specialize in offering only nearest real-time AV-sourced imagery, that is, continuously overriding the oldest data with the newest as a form of sliding window of streetscape imagery. This approach would therefore only require a constant amount of storage, and the incorporation of additional storage would only serve to extend the length of that window. Finally, the single greatest storage optimization of the rail system would be to avoid the storage of image data altogether. As an alternative or complement to passive monitoring, the on-demand economic model might incentivize AV owners or users to prioritize alternative vehicular route navigation, where cars would be encouraged to slightly detour from their route to collect required data. This framework is particularly well suited to contributors of the gig economy, where individuals pick up micro contracts to go and sense specific locations at specific times with specific sensor modalities. To wrap up for the sake of time, we encourage all listeners to carefully read this vision paper, as it further discusses the ethical risks and socio-technical ramifications of such a system and suggests means of preserving individual and collective privacy within our surveillance capitalistic society. With fleets of AVs poised to deploy locally, nationally, and globally, we recognize the opportunity to leverage these data as part of an informatics system with which we can better study, surveil, and digitally perceive the street and cityscapes of the world. We caution, however, that all reflect deeply and tread lightly, as such algorithmic solutions encroach upon human privacy and may be leveraged to modify human behavior. The ethical and philosophical ramifications of the use of AI as a whole reflects many of these themes, and through the proposed implementation of the rail system, we hope to enable future technological and societal progress while carefully considering the impacts of this envisioned system. Thank you, and I'm happy to take any questions.